Prompt injection. You've definitely heard the term, right? It's usually talked about like it's some clever trick, a kind of linguistic judo move you can pull on a super powerful AI. But today, we're not going to look at it as a trick. We're going to treat it as what it really is, a deep, fundamental vulnerability, one that isn't just a bug in the model, but is a direct result of the very architecture of large language models themselves. So let's break down exactly how it works from the inside out. So here's our game plan. We'll start by talking about why this is the #1 vulnerability out there. Then we'll get into how a transformer model sees the world as just one single stream of tokens. From there, we're diving deep inside the attention engine itself, seeing how attackers can actually hijack the model's focus and how that completely shifts the output. And that'll lead us to the big question: is this whole thing an unfixable architectural flaw? All right, first things first, let's really establish why this is so much more than just some clever trick. We're not talking about some theoretical attack you'd find in a research paper. We are talking about the biggest, most common security problem in AI today. Yeah, check this out. According to a report from Adversa AI, a staggering 35% of real-world AI security incidents come from simple prompts. Think about that for a second. This isn't some complex code exploit. The attack is literally walking right through the front door, using the exact input method the model was designed for. The open source security group OWASP puts it pretty clearly. They define prompt injection as a vulnerability where the model gets tricked into processing malicious instructions as if they were legitimate commands from the developer. And that's the absolute core of the problem. The model has no reliable way to tell the difference between the rules it's supposed to follow and user input that's designed to make it break those rules. And that really brings us to the central question we're trying to answer here. How is it that these incredibly complex, multi-billion parameter models can be so easily manipulated by, well, by a cleverly worded sentence? The answer, it turns out, is in their fundamental design. To really get this vulnerability, you first have to understand how a transformer-based LLM even perceives the world. This is the bedrock concept that makes the entire attack possible. And here's the key difference between an LLM and most other software you've ever used. Normal programs have separate channels for commands and for data, but a transformer, it just has one. The developer's system prompt, your question, and any malicious stuff an attacker throws in, it all gets flattened into one single continuous stream of numbers or tokens. To the model, it's all just context. This slide just lays it out perfectly. Look on the left, that's normal operation. You've got the system prompt followed by the user's query. Simple. But now look at the right. The attacker's injection just slides right in there, in the middle. It's not flagged, it's not put in a sandbox. It just becomes another part of the input that the model has to process like everything else. Okay, so if it's all just one big jumble of tokens, how does the model make any sense of it? Well, the answer lies deep inside the mechanical heart of the transformer, the self-attention mechanism. You can think of the whole process in 3 basic steps. First, all the text gets turned into these numerical vectors we call embeddings. Then, those embeddings get fed into the transformer block, and that's where the magic happens. The attention mechanism figures out the relationships between all the tokens. And finally, the model uses that new understanding to predict the most likely next token. The entire hack we're talking about, it happens right there in step 2. Now, to understand attention, you just have to get your head around 3 concepts: query, key, and value. The best analogy is a search engine. For every single token in the input, the model creates a query vector. That's the token asking, hey, what other tokens around here are important to me? Then, every other token generates a key vector. That's like the title of a web page saying, hey, this is what I'm about. And finally, there's a value vector, which is the actual content, the real information that token holds. It's a massive, complex system for weighing relationships. Okay, don't let the math scare you because the concept here is actually pretty intuitive. The model essentially multiplies the query of one token against the keys of all the other tokens. If a query and a key line up well, you get a high score, it's just a dot product. Then the softmax function takes all those raw scores and turns them into probabilities that add up to 100%. It's like giving the model a budget of attention to spend. This formula is literally how the model mathematically decides what matters most. So let's just walk through that one more time. The model multiplies queries and keys to get those raw relevant scores. It scales them down a bit, then softmax turns them into that attention budget. Finally, it uses that budget to create a weighted average of all the value vectors. What comes out the other side is a brand new vector for each token, but this one is now super enriched with context from everything else. And that context-rich vector is what the model uses to make its next prediction. Okay, we have all the pieces on the board. We know the model sees just one stream of tokens, and we know it uses the attention mechanism to figure out what's important. Now let's see how an attacker completely breaks this system. So, in a normal, healthy conversation, this is what you'd expect to see. When the model is thinking about what to say next, its attention scores are massively weighted towards the system prompt, its core instructions. As you can see here, maybe 85% of its focus is right where it should be, on behaving the way the developers intended. But now, look what happens when an injection is introduced. The malicious prompt is specifically engineered so that its key vectors will create super high-scoring matches with the query vectors the model is generating. It is mathematically screaming for attention. The model, just doing what it's programmed to do, shifts its focus, and suddenly the attacker's instruction is getting 85% of the attention, and the original system prompt is basically ignored. And this quote from the Cyberthrone just hits the nail on the head. The attack isn't a bug in a line of code. It's an exploit of how the system is supposed to work. The evil part is purely in the sequencing of the tokens, which hijacks the math. The vulnerability, as they say, is baked right into the architecture. So the attacker has successfully grabbed the model's attention. How does that actually translate into harmful output? Well, this is the final, crucial step in the chain. Remember that context-aware vector we talked about? The whole point of the attention mechanism is to build that thing. So when the attention scores get hijacked, that final context vector gets corrupted. It's now completely poisoned by the attacker's instructions. And since that corrupted vector is the only piece of information the model uses to predict the next token, well, you can see where this is going. The attacker is now steering the ship. This is a fantastic way to visualize it. It's the same principle as when you give a model a prefix like, the first person on the moon was. The model will almost certainly complete it with Neil Armstrong, because that's the most statistically likely outcome. An attacker does the exact same thing. They craft a malicious prefix that makes their desired harmful output the most statistically probable thing for the model to say next. And the consequences of this, as OWASP points out, are really serious. This isn't just about making a chatbot say something weird. This can lead to blowing past safety filters, leaking sensitive data, giving an attacker access to back-end systems through plugins, and even manipulating critical decisions in finance or healthcare applications. And all of this brings us to the final and, frankly, the most unsettling part of this whole story. If this problem is so fundamental to how these things work, can we even fix it? Well, here's the tough reality, straight from the OWASP team. Because these models are fundamentally probabilistic, they're just making educated guesses about the next word. And because they can't tell developer instructions from user data, a truly foolproof defense might actually be impossible with our current architecture. It's just a constant arms race. Attackers craft better injections, and defenders build better, but still imperfect, walls. So I'll leave you with this final thought. If the flaw is in the actual blueprint of the house, are we just patching cracks in a foundation that's always going to be a little shaky? Can prompt injection ever really be solved within the way we build AI now, or is real AI security going to require someone to invent a completely new architecture from the ground up? That's the multi-billion-dollar question facing the entire field right now.